So conversely, suppose that W is a subset of V, satisfying conditions 1 through 3, then by condition 2, the set W together with vector addition is a magma Now, as W is a subset of V, every vector U that is in the set W is also in the set V, where the set V together with vector addition is an abelian group, and so for every pair of vectors U and V in the set W, once again these vectors are also in the set V, where V together with vector addition is an abelian group, and so we have that vector addition is commutative, and for every 3 vectors U, V, and W in the set W, we have that vector addition is associative. Now, by condition 1, there exists the 0 vector in the set W, such that for every vector U in the set W, we have that U plus the 0 vector is the same as the 0 vector plus U, which is the vector U. Now, since the additive inverse of the multiplicative identity in the field is a scalar, by condition 3, we have that for every vector U in the set W, the scalar multiple, which is the additive inverse of the multiplicative identity times the vector U, is an element in the set W. And by the previous corollary, we know that this product is the same as the additive inverse of the vector U. And so for every vector U in the set W, there exists its additive inverse also in the set W, such that the sum of the vector U with its additive inverse in whichever order is the 0 vector, and hence the set W together with vector addition is an abelian group. Now, by condition 3, we have that for every scalar A and for every vector U in the set W, the scalar multiple A times U is in the set W. Now, once again, since W is a subset of V, we have that for every scalar multiple A times U, which is in the set W, that scalar multiple is also in the set V, where V is a vector space. And so the following conditions hold. A scalar will distribute over any 2 vectors. A sum of scalars will distribute over a single vector. A vector times a scalar multiple is the same as a scalar multiple of that vector, where that scalar is the product of the two scalars. And finally, the multiplicative identity of the field times the vector u is the same as the vector u. And hence, the set W is a vector space over a field F, or over the field F, with respect to the same operations as in the vector space V, and thus the set W is a linear subspace of the vector space V. And so now we have demonstrated both directions of the biconditional. Okay, so let's look at an example. Let V be a vector space over a field F. Then the set W, consisting of the zero vector alone, is a linear subspace of the vector space V, and it is called the trivial vector space or the zero vector space. So let's prove that this is a linear subspace. Clearly, the set W, which again is the set containing the zero vector alone, is a subset of the set V, as V is a vector space. It is an abelian group under vector addition, and therefore must contain the additive identity for vector addition, which is the zero vector. So W is a subset of V where the zero vector is in this set. And the zero vector plus the zero vector is the zero vector, which is in the set W. So W is closed under vector addition. And for every scalar A in the field F, we have that A times the zero vector is the zero vector, which is once again in the set W. And so W is closed under scalar multiplication. And so the trivial vector space is a linear subspace of any vector space. So recall that a basis for a vector space is a set of non-zero vectors that are linearly independent and span the vector space. There are no non-zero vectors which span the trivial vector space. So a basis for the trivial vector space is the empty set and the dimension of the trivial vector space is 0. Okay, so next we'll turn our attention back to quaternions. So recall that the set of quaternions is the set of all linear combinations x sub naught plus x sub 1 times I plus x sub 2 times j plus x sub 3 times k, where each scalar x sub I is a real number and I squared is the same as j squared, which is the same as k squared, which is the same as I times j times k, which is -1. And we have looked at the quaternions as a real vector space, in which case it is a 4-dimensional vector space. We can consider the quaternions either as an algebraic extension of the reals, including the multiples I, j, and k, real multiples of I, j, and k, or we can consider the quaternions as the coordinate space R4. Let's now look at some subspaces of the quaternions. So let H sub naught be the set of all quaternions of the form x sub naught plus 0 times I plus 0 times j plus 0 times k, where x sub naught is a real number. And then we shall soon call this the set of pure scalars. So clearly, H sub naught is a subset of the set of quaternions. The 0 vector, which has the form 0 plus 0 times I plus 0 times j plus 0 times k, is an element in the set H sub naught. For every 2 vectors x and y in this set, their sum is the sum of the form, the quantity x sub naught plus 0i plus 0j plus 0k plus the quantity y sub naught plus 0i plus 0j plus 0k, which is the quantity x sub naught plus y sub naught plus 0i plus 0j plus 0k, and this is clearly an element in the set H sub naught. So the set H sub naught is closed under vector addition. And for every scalar a, which is a real number, we have a times the vector x is a times the quantity x sub naught plus 0i plus 0j plus 0k, which is a times x sub naught plus 0i plus 0j plus 0k, which is once again an element in the set H sub naught. And so the set H sub naught is closed under scalar multiplication, and hence the set H sub naught is a linear subspace. Of the quaternions as a real vector space. So notice a basis for the set H sub naught as a vector space is the set B consisting of the vector 1, where this vector has the form 1 plus 0 times I plus 0 times j plus 0 times k, since for every vector in this set, this vector is equal to x sub naught times the vector 1, and x sub naught times the vector 1 is the 0 vector if and only if x sub naught is the 0 scalar. or the additive identity of the field of reals. And so H sub naught is a one-dimensional linear subspace of the entire set of quaternions. So since the set H sub naught is a one-dimensional vector space over the field of reals, we can consider H sub naught as the coordinate space of the reals, that is, the set H sub naught can be considered as pure scalars, the scalars of real numbers. So let's now look at another linear subspace of the quaternions. Let the set H sub p be the set of all quaternions of the form 0 plus x sub 1 times I plus x sub 2 times j plus x sub 3 times k, where x sub I is a real number. Then we'll call this the set of pure quaternions. Now clearly, the set H sub p is a subset of the entire set of quaternions. The 0 vector, which has the form 0 plus 0 times I plus 0 times j plus 0 times k, is an element in the set of pure quaternions. For every two vectors, x and y, in this set, the sum of the vectors x and y is the sum of the quantity 0 plus x sub 1 times I plus x sub 2 times j plus x sub 3 times k plus the quantity 0 plus y sub 1 times I plus y sub 2 times j plus y sub 3 times k, which is 0 plus the quantity x sub 1 plus y sub 1 times I plus the quantity x sub 2 plus y sub 2 times j plus the quantity x sub 3 plus y sub 3 times k, and this is clearly an element in the set H sub p, and so the set of pure quaternions is closed under vector addition. Now for every real number a, and for every vector x in the set of pure quaternions, we have that a times the vector x is a times the quantity 0 plus x sub 1 times I plus x sub 2 times j plus x sub 3 times k, which is 0 plus a times x sub 1 times I plus a times x sub 2 times j plus a times x sub 3 times k. And once again, this is an element in the set of pure quaternions, and so the set of pure quaternions is closed under scalar multiplication. And so the set of pure quaternions is a linear subspace of the entire set of quaternions. Now a basis for the set of pure quaternions is the set B, consisting of the vectors I, j, and k, since for every vector in this set, that vector is a linear combination of the vectors I, j, and k, and this linear combination x of 1 times I plus x of 2 times j plus x of 3 times k is the 0 vector if and only if x of I is 0, the 0 scalar for every index I. And so the set H sub p of pure quaternions is a three-dimensional linear subspace of the four-dimensional vector space of the quaternions.